Okay, thank you all for tuning in for our talk, Modeling Unveils Optimal Aid Use Strategies. A bit of context to begin with. Automated aids are available to assist us in a variety of signal detection tasks, like, for example, when we get a call from an unknown number, we can be assisted by automation, like in this case where it's giving us a diagnostic cue saying that we're likely getting spammed. These kind of automated aids can also be implemented in other settings, such as to assist practitioners during medical diagnosis and to assist navigators while shifting lanes during driving. And the general point of having these automated aids is to help us do better than we would by ourselves, and a little bit more specifically to increase our sensitivity or ability to distinguish between normal noise events of the world and critical signal events of the world. What we have happening during this aided process is that we have both agents engaged in independent process of signal detection. So they gather evidence for signal in the environment encoded mentally as a decision variable X, and they gauge this variable against an evidence cutoff to see if they will elicit a yes judgment. During aid detection, the aid communicates its decision to the operator, who can then use this for an aided judgment. And for this presentation, we'll focus on automation that provides simple binary diagnostic cues, like in this case where we're simply saying signal present or signal absent. Now, we want to arrive to maximal levels of aid sensitivity as best as we can possibly do with this kind of automation. We need to integrate the cue that it is giving us to our detection process. So, for example, if it gives us a signal present judgment, we should shift our cutoff to be more liberal, so we don't require as much evidence for a yes judgment. On the other hand, if it gives us a signal absent judgment, we should shift it to be more conservative instead. And here, the extent to which we shift our cutoff is giving us estimate of dependence, how much we rely on automation. To derive optimal levels of aid sensitivity with this model, we need to calibrate our dependence to the probability of noise or of signal each trial, which is partially given by the variance of the cue that the aid is giving us, and by the reliability of the aid, meaning to say that if the aid is more reliable, we need to rely more on it. Again, this is a strategy we should adopt if we want to do things as best as we possibly can. Empirically, however, it doesn't seem like this is what happens. Here we have data from a study we ran in 2022, where we're looking at is posterior distributions of sensitivity estimated through D prime. Here in gray, we have how participants did when they completed an unaided block of trials by themselves. And here in pink, we have how participants did when they had binary automation assisted in the process. And as you can see, they did better, so they do benefit from having the aid. But also, here are the estimations of optimal aided performance through an optimal CC strategy. And as you can see, they fell way short of this, which is telling us that this optimal strategy is not what they're engaging on. However, if we want to increase the quality of aid use in applied settings and best guide system designers, we'd like to know what it is that operators are recruiting empirically. So here are some potential options. The first is what we call a slavish contingent cutoff strategy. This is the same CC process we discussed, but it just assumes that the operator doesn't shift their cutoff as much as they should if they were optimally depending on automation. Another possibility is that rather than integrating the cue to the detection process, they just engage in an all or nothing discrete deference or DD strategy. This essentially means that for some trials they just do what the aid tells them, and for the rest of them they act as if the aid wasn't present and just do an unaided process of detection. And this strategy might be a little bit easier in terms of cognitive load for the operator, but since it's discarding part of the evidence we have available for our detection judgments, it also cannot derive optimal levels of sensitivity like a CC strategy can. A third strategy is sort of in the middle of the two. It assumes that for some trials, the operator simply does what the aid says, and for the others, they do engage in a process of contingent cutoff strategy. In this talk, we're going to review data from 4 experiments where the predictive fit of each of these strategies was compared, Across experiments, we recruited our participants from the prolific academic pool, and they completed all of the experiments entirely online. Here we have a sample unaided trial from experiment 1. We gave it a numerical signal detection test where they sampled 4 readings each trial. The cover story is that these readings were indicative of levels of contamination for chemical batches, and participants' job was to decide if they should reject the batch or keep it. We told them that generally when the batches were contaminated, they would yield readings above 500, so in that case they should reject the batch. Each trial, these readings were being sampled from either a noise or a signal distribution corresponding to uncontaminated or contaminated events. And because there was some overlap between these distributions, some signal events could produce readings below 500 and vice versa for noise events. So we told participants some errors were unavoidable. This again is a sample unaided trial. Aided trials were the same as these trials, but participants received binary diagnostic keys, like in this example. And this aid arrived to its decision through a similar sampling process, so it also made some errors. We programmed this aid to be 93% reliable for all experiments except experiment 2, where it was 84% reliable. To compare the predictive performance of the strategies we reviewed, we fed the data with Biscoe Bayesian models. We allowed parameters to vary from person to person and estimated the mean levels hierarchically. And for unaided trials, we assumed the same process for all models. Essentially, we assumed that they used the average of the 4 readings we gave them as their decision variable each trial, but that the estimates of the average were contaminated by zero-centered Gaussian error, which gave us a parameter to estimate sensitivity. Then we assumed that they gauge this average against a cutoff to arrive to their unaided decisions. The strategies for aided trials differ depending on the model. For the CC model, we assumed that participants shifted their cutoff in the direction of the cue given to them by the automation with a certain magnitude. For the DD&C and mixture model, we assumed that participants differ to the automation with a certain probability, and when they didn't differ to the automation, they engaged either on an unaided process of detection for the DD model or on a CC process of detection for the mixture model. And these models predicted different patterns of mistakes in terms of complacency, so when the human operator would agree with erroneous automation feedback. Specifically, the CC model predicts that we're going to make these mistakes when there is high ambiguity in the readings we're getting, so that when they are close to the 500 cutoff. But when we're getting very obvious numerical readings that are very high or very low, we shouldn't make these obvious mistakes. The DD model assumes that participants are deriving non-stimuli-driven responses when they are deferring to automation, so it predicts that we're going to make these kinds of mistakes evenly across ranges of numerical readings. And finally, the mixture model allows for some of these obvious mistakes to happen, but predicts that we're going to make more of these mistakes when the evidence we're sampling is more ambiguous. Across 4 experiments, we compared the predictive fit of each strategy through base factors and DIC scores, and we generally saw decisive evidence in favor of either the mixture or pure DD strategy, which overall is telling us that empirical performance is more consistent with the strategies that entail discarding part of the information we have available for detection, rather than with the more inherently appropriate CC strategy. We also conducted empirical performance checks to see how best fitting models predicted empirical data for all experiments. Here we have data from experiment 1, and what we're looking at is yes rates on the y-axis, how often people said yes, across blocks on the x-axis unaided and aided blocks, and for 2 different panels representing an experimental manipulation for this experiment. We have empirical signal trials on black on top and empirical noise trials on white on bottom. And here this cross match represents the mean predictions of the best fitting mixture model. And what we see here is that those predictions are falling within the 95% Bayesian credible interval across all conditions or trending towards it. What this is telling us is that the best fitting model, in this case a mixture strategy, is accurately predicting what participants are doing empirically. And we saw this kind of pattern for accurate, although somewhat imperfect, predictions across all experiments. Now here we have estimates of the dependence parameters that tells us how much participants relied on automation, again for experiment 1. First over here we have posterior distributions of criterion shift delta C, and the first thing to notice is that this fell very close to 0, which overall tells us that participants didn't quite shift their cutoff that much when we assumed a CC process. Over here in yellow, we have optimal estimations of criterion shift, and as you can see, empirical measures fell way short of this, which is generally telling us that participants disused the automation. Now, when we assumed deferral to the aid, we're seeing a similar pattern, with estimates of the probability of deferring very close to 0, which is telling us that overall participants didn't quite use the automation that much, either when we were assuming a CC or a DD component of the strategy. We saw similar trends across all experiments, and what we're seeing here overall is this better fit for the suboptimal models and evidence of widespread aid disuse. It also clues a little bit into how to increase the quality of aid use. Specifically, we'd like participants to engage in this information integration process under a CC strategy more, but we also need them to dramatically increase their dependence on automation. And in the event they're unable to do that, it might actually be beneficial for performance to just rely more on the more sensitive agent, either the automated aid deferring to it with a higher probability or the unaided human operator. An implication for applied settings is that because participants recruit these suboptimal strategies, the value of automation implementation is going to be undercut in anti-realistic scenarios. And future research might aim to uncover situations in which we might be more or less concerned about the quality of aid use, such as when we vary the sensitivity of agents involved, making the aid more reliable or making the task difficulty more difficult. We leave you with the following takeaway and with QR codes to the empirical reports for some of the experiments we discussed, and we look forward to hearing your questions. Thank you.